We have now seen a conceptual model for planning, namely the state transition system. This helped us formalize the problem we are trying to solve in planning. A technique that is used almost everywhere in planning and in many other areas of AI is called search, and this is what we will be looking at next. Before we go into the details of search algorithms, I briefly want to talk about the types of problems we will see on this course, namely toy problems versus real-world problems. Toy problems are characterized by a description that is concise and exact. The description being concise allows me to describe the problem in one slide and quickly. The description being exact means there shouldn't be too much ambiguity about what the problem is trying to do. Toy problems are often used for illustration purposes, for example, on this course. They are also used to compare the performance of different search algorithms. Toy problems have two interesting properties, namely they are rich and simple. By rich, we mean they're anything but trivial to solve, and by simple, I mean they can be described easily and precisely. Real-world problems tend to be very different. To begin with, there is no single agreed-upon description for most real-world problems. That means if we were to use real-world problems in this course, I would spend a lot of time describing what the actual problems is and describing the details that need to be addressed in each problem. However, toy problems are good as mental exercises, but real-world problems, people care about the solutions of those. The missionaries and cannibals problem we have seen earlier clearly falls into the category of toy problems. Now, before we go into search algorithms, we need to characterize what constitutes a search problem. And here are the four components that characterize a search problem. The first component is the initial state. This is simply the state of the world from which we start our search. In the missionaries and cannibals problem, this was the state where all the missionaries and all the cannibals and the boat were on the left-hand side of the river. Next, we need a set of possible actions. Not every action will be applicable in every state, so we will also need to define the applicability conditions for actions in states. We can define the actions through a successor function. A successor function maps a state into a set of pairs of actions and state. So for each state of the world, the successor function maps it to all those actions that are applicable, together with the states that result from the action being applied in the original state and leading us to this new state. Together, the successor function and the initial state span a state space, which corresponds roughly to the states transition graph we have seen earlier. The state space is a directed graph with states as nodes and actions as labels on arcs. The third component of a search problem is the goal. This can be either an individual state, in which case we have just one unique goal state, or in general we can have a function that tests whether a given state is a goal state or not, which allows us to have many different goal states. A solution to a search problem is simply a path in the state space from the initial state to a goal state. The final component of a search problem is the path cost function. This simply assigns a cost value to each possible path in the state space. We use this when we're doing optimal search. When we're looking for an optimal path, we're looking for the path with the lowest cost. A simplification that is often used in planning is that each action has a fixed cost, and that the cost of a path is simply the sum of the step costs, the costs of each action. Now, you will have noticed that there are some similarities between what we've just defined and state transition systems, and the next quiz will give you a little time to think about those similarities and differences. Going back to the missionaries and cannibals example, let's try to define this as a search problem. So we need to define the four components, which were the initial state, which was given to us as part of the problem. And the third component was the goal state, which was also given to us as part of the problem. Then the fourth component is the path cost function, and there we simply assume that every step has the same cost. So the only thing that is slightly more complex is the successor function, and we can define this as a table as shown here. So what this table does is simply enumerate all the mappings of states to set of action state pairs. What we have on the left-hand side is a state. So this is the initial state as defined in the problem. And I'll decipher this for you quickly. This has two components. It says what's on the left-hand side and what's on the right-hand side. On the left-hand side, we have the 3 missionaries, we have the 3 cannibals, and the boat. And on the right-hand side, we have no missionaries and no cannibals initially. So that is the initial state. We describe everything that's on each side of the river. This is mapped to 3 pairs. 1, 2, 3. Each of which consists of an action and another state. So let's look at the first one. In the first case, we ship 2 cannibals across the river. And this gives us on the left-hand side 3 missionaries, 1 cannibal, because we've shipped 2 cannibals across. On the right-hand side, 0 missionaries and 2 cannibals, plus the boat, which is also now on the right-hand side. Altogether, we see there are 3 different pairs here, because there are 3 applicable actions in the initial state. In the next row, we have a different state, and we again define what can be done in the state. These are the 2 actions, and the resulting states that we get if we apply these actions. This is actually the same state that we've looked at just now. This state here became the state there. So we need to do this for the whole set of states that are available, for the whole state space, which means we need to go through a whole list of states and define where we can go from these states. And if we had completed this table, we had defined the whole state transition function, and this concludes the definition of the search problem. In contrast to this toy problem, we will now look at a real-world problem, namely touring in Romania. What you see here is a rough map of the country with some of its major cities. To define touring Romania as a search problem, we again have to define the 4 components of a search problem. So let's start with the initial state. Suppose we are in the city of Arad. That's where we start our tour of Romania. The next thing we need to define are the possible actions that we can take in this problem. Since we are looking at a map, it suggests that we can drive from one city to another. But presumably when you're touring a country, that's not all you want to do. You probably also want to do some sightseeing, or you need a hotel, so you need to check into that hotel, you need to book a hotel. There are many different types of actions that you want to do when you tour a country. And you can see this is a real-world problem. We already have the first problem, deciding what the possible actions are. The same applies for the goal. When you're going on holiday somewhere to tour a country or a region, what is your actual goal? Well, presumably you want to end up in the same state that you started off, namely at home. So that can't really be the goal. You want to have something else that you need to describe as your goal, something that happens along the way. But it's very hard to describe, because this is a real-world problem. What is a little bit easier is probably the cost that is associated with each action, and that will mostly be time and money. As a side remark, the touring in Romania problem is taken from a famous AI textbook by Russell and Norvig, and if you want to learn more about search, I recommend that you have a look at this book. The reference to this book will be given on the course website. So what you have just seen is that problem formulation is itself a complex problem, and it's the problem of defining the 4 components of a search problem. In problem formulation, we have to decide what actions we want to consider and what states we want to consider in the world. Probably the most difficult decision there is, at what level of abstraction are we looking at the world? What detail do we want to take into account and what detail do we want to omit? So looking at the touring Romania examples, we could define actions that describe how we drive a car, that say we have to turn a steering wheel by 1 degree left or right, and we have to move our foot from one pedal to the other. But this would probably give us too much irrelevant detail, and there's a lot of uncertainty involved in that too, so we probably don't want to go to that lower level of detail. Also, if we try to solve our problem at that level of detail, we would come up with a solution plan that has many, many steps. If we define the problem at a higher level of abstraction, say we consider actions that drive us immediately to another big city, then we have the problem that we need to decide how to execute such an action when we come to plan execution. Also, if this is the level of abstraction we consider, driving to another city, we can't really talk about things we do in between 2 cities. So Deciding at what level of abstraction we model our actions and states is probably the most important decision in problem formulation. But to help us with problem formulation, there are a number of assumptions that search engines and planners often make, and if we take those into account during problem formulation, we may have a much easier task. The first assumption is that we have a finite number of world states. This implies that we cannot have continuous variables in those states, as this would automatically give us an infinite number of states. Then we will assume that the world is fully observable, which means everything that is relevant to us in the state of the world can be seen and will be known to the algorithm, to our planner that we're using. The next assumption is that the actions that we're using are deterministic, which means each action has one well-defined outcome. There's no uncertainty which state we will be in after we apply an action. The final assumption is that the world is static, which means there are no events. So nothing happens that we don't do. Only the actions that we do modify the state of the world. So these are assumptions about the environment, but we will also make some other assumptions that are useful for planning. The first one is that we have restricted goals, and that means that our goals are either given to us as a single state that we want to be in, or a set of states that are all goal states. The second assumption is that the solution we are looking for is a sequential plan. So a solution is a linear list of actions. There's no parallel activity in our plans. We shall also not consider time explicitly, but only implicit, which means activities will not have a duration for the time being. And the final assumption is that we're doing offline planning. That is, the state transition system which underlies our planning process is not changing while we are doing the planning. Okay, time for another quick quiz to give you time to think about this.